This example leads to an important term that you should know. The 4 events that are created in parts A, B, C, and D, because they form the full sample space, they're said to be exhaustive. They exhaust all of the possible outcomes. All possible outcomes. That's a term you'll encounter sometimes. A question might ask something like, if it'll describe 2 events, can you prove that they are exhaustive? So just kind of know what that means. Let's look now a little bit more at the case of dependent events. With 2 dependent events, the outcome of one does affect the probability of the other, so you have to account for that whenever you're determining the probability of that intersection. You're still going to use multiplication. An intersection is still an AND problem and does still lead to multiplication. You just have to modify the second probability to take into account what happened with the first event. So here what we say is that the probability of A and B, the intersection, is equal to the probability of the first event. You account for that one, and then you multiply by the probability that the second occurs given that the first has occurred. So this is the change right here. It's still multiplication, but you take into account the impact that the first event had on the second. In a situation with dependent events, one thing you might just want to make a note of is that tree diagrams work very well. Just for organizing all the different numbers, you tend to have more numbers to keep track of on these problems because of all the different cases involved. Let's look at an example. Let's just extend actually that previous example. In the previous example, we said that Jiri had a 70% chance of hitting the target. Let's keep that. And we'll still call this P of J. But let's say that they're no longer going to fire simultaneously. Instead, Jiri's going to go first. And then whether or not he hits the target, maybe that would affect Benita. Maybe instead of having the same probability regardless, let's say she gets a little bit nervous. And so after Jiri fires, let's say that if Jiri hits the target, then Benita hits 50% of the time. And if he misses the target, then maybe she's a little bit more confident. Let's say if he misses J prime, then Benita hits the 80% that was given in the previous problem. Since we have more numbers to keep track of here, a tree diagram might help. For the first event, there are 2 possibilities. Either Jiri hits or Jiri misses. We know that this has a 0.7 chance and this has a 0.3. From there, for each of these, either Benita hits or Benita misses. So we have the same outcomes that can occur, but with different probabilities. If Jiri hits the target, then Benita has a 50% chance of hitting and a 50% chance of missing. If Jiri misses, then Benita hits 80% of the time, and that would mean that she misses 20% of the time, because these 2 need to add up to 100% for her portion. So then we get 4 different outcomes with 4 different probabilities, or I guess really just 3 different probabilities. A typical question might ask something like, find the probability that Benita hits the target. And this is no longer the simple 80% that it was in the original problem. Instead, recognize that there are 2 different ways that this can occur. One option is right here. Jiri hits and Benita hits. The other option is that Jiri misses and Benita hits. So to find the probability that she hits the target, we need to account for both of those. To get this probability, the probability that they both hit the target, we need to multiply along those branches of the tree diagram. 0.7 times 0.5 would give 0.35. Here, we're finding the probability that the first person misses and the second person hits. Multiply the probabilities. 3 times 8 is 24, so 0.24. So then the probability that Benita hits the target would come from 2 different possible outcomes. This one, Or, so we'll add this one. We'll add the two different parts of the tree diagram, 0.35 for one possibility plus 0.24 for the other possibility. So we get a probability that she hits the target as being 0.59, or a better answer would be 59%, since the original problem was stated with percents. There are two more rules that you need to know at this point. These are both in the formula book, and they both apply to compound events or combined events. The first is called the addition rule, and it's for a union, meaning just putting two sets together, including the overlap. The rule here says that the probability of A or B, a union B, is equal to the sums of the probabilities of the individual sets. But you have to pay attention to that overlap. If you just add these two sets together, you count the overlap twice. We do want to count it, but we don't want to count it twice, so we'll subtract that duplicate. Subtract the probability of A and B. And this is what you're doing on the Venn diagram when you add up all the numbers in one circle plus all the numbers in the other circle. It's counting that overlap twice. So you subtract it once so that one counting of it will remain. And then also, a special case of this comes up if you have mutually exclusive events. Mutually exclusive events are ones where there's no overlap, meaning that the events can't both happen simultaneously. For example, if we're talking about drawing cards out of a deck, the event of drawing a 10 is mutually exclusive from the event of drawing a 6, because if you draw a single card, there's no way it can be both a 10 and a 6. So those would be mutually exclusive events. In that case, when you're doing this addition rule, there's no overlap to be subtracted, so the rule could be simplified this way. The probability of A or B is equal to the probability of A plus the probability of B. The overlap is a 0, so you can just leave that one out. It looks like a separate formula, but of course it's the same thing, just a special case of it. A Venn diagram for mutually exclusive events is going to have two disconnected circles. Often you don't know that at first. You'll begin with a Venn diagram that looks like this one up above, but then as you get to looking at the numbers, you'll find that this inner section has to be a 0, and so it could have been drawn separately. The last thing for today is to look at these two on your own problems. One of these has independent events and the other one has dependent events, so begin by identifying those.